A return rocket stands on Mars under a cold orange sky. And the question is whether that rocket is a real way home years after the crew left Earth. The hard part is not only reaching Mars, and leaving it again may be harder after the surface has had years to work on the equipment. The return rocket has waited in silence through cold and dust, and no human has ever launched from Mars, and no crew has yet trusted an exit system already parked on another world. The return may need local propellant and a narrow window to work. It also needs a body changed by years away from Earth, and an orbital handoff that still holds when the moment arrives. If that chain is strong, Mars can remain exploration. If that chain is weak, settlement can become one way in practice even when the plan still says round trip. By the end of this video, you will understand why the way home from Mars is not one journey but a chain, and how a weak link in that chain can turn exploration into practical exile. We will work through that chain. No one needs to claim Mars return is impossible. One narrow question matters. What has to be true before a crew on Mars can honestly say they still have an exit? If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. We usually picture a Mars mission as a clean sequence. Earth launch, months of interplanetary flight, then touchdown on Mars. The crew does its work, and departure follows later when the surface mission is finished. But that picture hides the real constraint. The return trip cannot be added at the end. It has to be built into the mission before the first crew commits their lives to it. Let's slow down here, and a round trip is not a slogan. The burden is proof. The phrase means the path home exists in real machinery, with verified fuel and timing, before anyone is placed beyond easy rescue. It also means the crew's medical condition still fits the route they are being asked to trust. On Earth, a journey can often be improvised backward. If a vehicle fails, another can be brought in, and if a schedule changes, the route can be adjusted. The system around you absorbs the trouble. Mars does not work that way, and Mars is a planet, not a remote base on Earth. For much of its orbit, Mars sits hundreds of millions of kilometers away, and the delay is not only in communication, the delay is in physics. So the first correction is simple. Getting to Mars is not the first half of a return trip, because the first landing only begins the return chain's test against reality. That chain begins before launch from Earth. Some part of the exit system must be designed and transported before the crew ever needs it. Then it has to land, survive checkout, and remain preserved on the surface, and some part of the propellant story must be solved. Some calendar must line up. Some vehicle in orbit or on the surface must still be alive when the crew needs it, and this is where the word home becomes technical. Home is not just Earth in the sky. Home is the sequence of events that can move a crew from the Martian surface to Mars orbit, from Mars orbit to interplanetary space, and from interplanetary space back into Earth gravity. We can say this without turning Mars into doom bait, and Mars return is possible in principle. Engineers have studied it for decades, and the point is not that the door cannot be built. The point is that the door has to remain open. A Mars crew may live inside a habitat, and that broad survival problem belongs to another question. Here, the habitat is background, and the exit is foreground. Every system matters only as it keeps the path home credible. Think about what that means for mission design, and the return system is not a luxury. The exit cannot be a hopeful later phase. The return plan is the moral and engineering condition that keeps the mission from becoming exile. Now look at the difference between arrival and return. And arrival is driven from Earth. Earth launches the crew, and Earth tracks the spacecraft, and Earth prepares the mission. Earth can test hardware under controlled conditions before it departs. Return begins under weaker conditions, and the crew is tired, and the machines have aged. Dust has reached seals and joints across months of Martian nights. Spare parts are limited, and the decision to leave may be forced by a medical problem, a system failure, or a calendar that cannot be negotiated. So the return trip starts early. Before a crew leaves Earth, the mission must answer a question that sounds almost too obvious to ask. If they need to leave Mars, what exactly takes them off the surface? The answer is not a vague capability, it is a specific sequence that has to remain real after the crew has already depended on Mars for a long time. The chain begins with a vehicle and verified propellant. It has to reach the right orbit, meet the transfer path, and return through Earth entry with a body that can endure it. So the first link in the chain is not philosophical, and the answer is physical. The hard part is keeping every link true after the landing has already happened. Somewhere on Mars, before the crew can trust the word round trip, there has to be a machine that can lift them from the planet, and once we see that machine clearly, the whole problem changes shape. Now this is easy to miss because the outbound mission looks more dramatic, and Earth launch is loud. Mars landing is violent, and the return chain is quieter, and readiness states and verified inventories make it real. Orbital geometry and medical margins decide whether it stays real, and quiet does not mean secondary. The quiet systems are often the ones that decide whether a mission remains reversible. We also need to separate two ideas that are often blurred. A settlement can be permanent as a community while still preserving individual return, and a mission can be temporary as a plan while still trapping individuals if the exit chain fails. The ethical line is not the word settlement, it is whether the choice to leave remains practical. Now we can put a sharper test on the word return. If the crew has to trust a vehicle, then the vehicle cannot be only a design in a slide deck. If the crew has to trust a window, then the calendar cannot be treated as an administrative detail. If the crew has to trust medical recovery, then the mission cannot pretend the body that left Earth is the same body that comes back. Wanasta explains why the return trip starts before departure. It starts in the architecture review, in the mass budget, and in the decisions planners make about what must be true before the crew commits to Mars. Has the ascent vehicle already been sent, and has the escape system proved itself in enough of the right conditions to be trusted? Let's make that concrete. A first crew may spend months traveling outward and many more months on the surface. During that time, the exit system is not waiting in a clean hangar. It is waiting inside the mission. It has to remain visible to operators, inspectable by the crew, and honest enough that nobody confuses a plan with a capability. So the question is not just, can we design a Mars return? And the more useful question is, when does the return become real? Is it real when the blueprint exists? When the hardware lands? When the tanks are full and the launch window is near enough and the crew's condition still fits the ascent limits? Those are different thresholds, and each one changes the moral status of the mission in its own way. We should be careful here, and exploration has always involved risk, and the first ocean crossings did not have perfect rescue plans. Early polar expeditions moved beyond easy help, and spaceflight itself began with very little margin by modern standards. But Mars is different in one crucial way. The distance and timing are so large that rescue is not a backup plan in the normal sense. The mission must carry its own reversibility. The return path has to come with the crew, not arrive afterward. Here is the adult version of the opening question. Not whether people are brave enough, and not whether Mars is worth studying. The test is whether the systems preserve a genuine option to leave after Mars has stopped being a destination and become the crew's daily environment. And that test belongs at the beginning, not the end. And if the way home is weak, every later success sits on a quiet uncertainty. The landing can be perfect, and the first habitat can work. The first science campaign can be extraordinary. But if the exit remains partly assumed, the mission is still asking people to accept a different bargain from the one printed on the label. So before we talk about the later links in the chain, we need to hold one image in mind. Somewhere in the architecture, there has to be an exit that is more than hope. On Earth, a failed journey often has outside help, and another vehicle can arrive, and a hospital can receive the injured. A spare part can be driven across a continent. Even remote places remain inside an industrial civilization. Mars sits outside that safety net, and a radio signal can cross the gap, and a repair crew cannot. A plan can be changed on Earth, but a missing engine on Mars cannot be wished into the cargo hold. So the first correction is this: getting to Mars is not the first half of coming home. Arrival starts a second test, and that test asks whether the exit chain has remained real. That chain begins before departure from Earth. Some return hardware has to be launched or pre-positioned, a fuel plan has to be selected, and some mission rule has to protect the exit from becoming a later hope rather than a present fact. The word home becomes technical here. Home is not just a blue point in the sky. Home is a sequence: surface ascent, departure into interplanetary space, and finally Earth re-entry by a body still able to endure it. We can hold two truths at once, and Mars return is possible in principle, and engineers have studied credible architectures for decades. But possible is not the same as preserved. This video is not the broad question of how people live on Mars, and that question belongs beside this one, not inside it. Food and pressure matter here when they affect the route out. Shielding, dust, and daily survival matter for the same reason. The exit is the foreground, and the habitat is background. And the question is not how a crew keeps living on Mars. The question is what lets them stop living there if the mission requires it. That distinction changes the ethics. A settlement can be permanent as a community while still preserving the return of individuals. A temporary expedition can become practical exile if the return chain fails. Let's use a simple standard, and it is not perfect safety because spaceflight has never offered that. The standard is a credible path by which people who went to Mars can still leave Mars when the mission says they can. The path has to be credible before the crew is committed, and once people are on the surface, the exit system is no longer a diagram, it is part of their condition of life. Think about the direction of dependence, and the crew cannot use a launch window if the vehicle is not ready. They cannot use the vehicle if propellant is not verified. They cannot use the propellant if storage has failed. None of that requires a dramatic accident, and a margin can shrink, and a valve can age. A schedule can slip, and a medical issue can change what risk is acceptable. The way home can become less real one ordinary constraint at a time. That explains why return has to be treated as an architecture, not a closing scene. A mission that waits until the end to prove its exit has placed the proof in the most unforgiving part of the journey. Now the useful question is not whether Mars is inspiring or hostile. It is whether each link has moved from assumption into a condition the crew can trust. Before Earth launch, the return architecture has to appear in the mass budget. It has to appear in the schedule. It has to appear in mission rules that say which resources cannot be consumed for convenience. A surface plan that quietly borrows from the return system is not only an engineering risk, it is a promise risk. It changes the meaning of consent because the crew accepted one mission and may end up inside another. The word later is dangerous on Mars, because later makes no commitments and holds nothing in reserve. Later with what vehicle and in what state of readiness? Later with what fuel, under what window, and with what medical condition? Each question pulls the return promise out of language and into physics. Integration is the unglamorous part, and one team may solve ascent, and another may solve propellant. Another may solve navigation, but Mars does not experience those contributions as separate documents. The crew experiences them as one chain, and a gap between any two links is not a filing problem, it is an exit problem. So we should treat a round trip as a system state. A mission deserves that phrase only when the vehicle and fuel are ready, the timing and orbit match, and the transit plan can actually move people home. Here is the adult version of the Mars question. It is not whether humans are brave enough to go, it is whether the architecture respects the full cost of preserving the choice to leave. One more detail belongs here. The return chain is easier to neglect because it is invisible when everything is going well. A habitat problem announces itself, and a food shortage announces itself, and a rover failure interrupts the day. But a weakening exit can remain abstract until the mission suddenly needs it. That is why return capability has to be monitored like oxygen pressure, not remembered like a future milestone. We need the way home to be a living system, not a ceremonial promise kept in the background. And once we phrase it that way, the first object becomes obvious. Somewhere on Mars, before anyone can honestly trust the word return, there has to be a machine that can lift a crew off the surface. On Mars, that exit begins with a rocket. A rocket on Mars is not just a rocket. The vehicle is the crew's lifeboat, standing in an environment where no launch team can walk out and repair it. NASA's robotic Mars sample return plans make the basic idea visible, and even returning a small container of samples requires a Mars ascent vehicle. It would be the first rocket launched from the surface of another planet. But the sample return rocket is only an analogy, and it would lift a small payload. A human Mars ascent vehicle has to lift people inside a pressurized volume. It also has to carry life support, guidance, and enough docking capability to reach the right orbit with margin. Let's name the constraint plainly, and Mars helps a rocket in some ways. Gravity is about 38% of Earth's, and the atmosphere is thin, so the velocity needed to reach orbit is lower than it is from Earth. That sounds like a gift, and the gift is real. But measured against the actual return problem, it is a smaller advantage than people usually imagine. On Earth, launch is surrounded by industry, and roads and cranes surround an Earth rocket before flight. Clean rooms and launch teams surround it too. The support system is everywhere. On Mars, the crew has what they brought, what was landed ahead of them, and what still works. And there is the difference. A Mars ascent vehicle may have to wait for months or years, and it waits through dust, it waits through cold nights, it waits through thermal cycling and low pressure. It also waits under radiation, in a surface environment nobody has ever used as a human launch site. And here is the uncomfortable part. The vehicle is most important at the moment when it may be least convenient to trust it. If the crew needs to leave, the rocket cannot merely look intact, it has to function. We can test parts on Earth, and we can simulate dust and cold, and we can run vibration campaigns and thermal vacuum tests. But a crewed launch from Mars has never happened. The first full proof would happen when people are already depending on it. The robotic sample return analogy matters because it shows how many pieces exist even at small scale. Surface launch is not the whole return. It only places the payload into Mars orbit, where another vehicle has to find it, capture it, and send it home. For a human crew, the same idea becomes heavier. The ascent vehicle has to reach the right orbit with living people aboard. Then those people must transfer into a return system that can sustain them for months. So when we ask whether Mars settlers can come home, we are not asking whether rockets work. We are asking whether a specific rocket can sit on Mars, remain ready, and launch successfully when the crew's route back to Earth depends on it. Now picture the psychology of that, and every day on Mars, the ascent vehicle is more than hardware. It marks the boundary between settlement and exile, and keeps the word temporary meaningful. If the vehicle is healthy, Mars is still a place the crew is visiting or building from. If the vehicle is compromised, the landscape may look the same and the mission documents may still say return, but the practical status of the crew is different. So the rocket waiting on Mars is the emotional center of this question. The vehicle waits quietly, and it may never be used until the final days of the surface mission. But without it, Earth is only a direction, and a rocket cannot leave on intention alone. It needs propellant. Another reason the ascent vehicle matters so much, and full rehearsal is hard for the complete event. Engineers can test components on Earth, such as engines, control systems, and seals. But the integrated act of launching humans from Mars includes the Martian surface as part of the test environment, and that environment cannot be brought fully into a laboratory, and because the vehicle is used late, it carries accumulated risk. A machine used on day one has less time to be damaged by waiting, while a machine used after a long surface stay has to remain healthy while the rest of the mission consumes attention. The lifeboat has to survive neglect, because nobody can spend every hour caring for only the lifeboat. Now the useful question is not whether Mars ascent vehicle sounds difficult. The useful question is what the vehicle has to prove while nobody can give it Earth-like care. A launch vehicle on Earth receives constant attention until the final hours. A Mars ascent vehicle may need to be boringly dependable after a long period of exposure. That word, boringly, matters, and lifeboats are not supposed to be heroic. They are supposed to work. The crew should not have to wonder whether a valve has been changed by dust, whether a seal has hardened through thermal cycling, or whether a tank has kept its condition through months of cold. Let's separate the help Mars gives from the help it does not give, and lower gravity means the rocket needs less velocity than an Earth launch vehicle. The thin atmosphere reduces some aerodynamic loads. Those facts are real, and they are why a Mars ascent vehicle can be much smaller than an Earth rocket carrying the same number of people. But the missing infrastructure is just as real, and there is no nearby factory, no replacement booster in storage. The launch site is a planet that has never supported human departure, with no recovery fleet and no pad team to walk the vehicle down. So the rocket becomes a concentration of trust. It must carry propulsion, guidance, and life support, and then meet the next vehicle in the right orbit. If it reaches the wrong orbit, the problem is not just fuel efficiency. It is whether the crew can be found and received before consumables and margins begin to close. We can use the sample return vehicle as a scale lesson, not as a direct comparison. Returning a small cache of samples already needs a rocket from Mars and a capture event in orbit. That is for a sealed container with no life support requirement. A human vehicle changes the stakes entirely. People need sustained pressure and thermal control and enough abort logic to survive a rendezvous that does not go perfectly. Here is where the word waiting becomes important, and the ascent vehicle is not only a rocket, it is a stored promise. Its most valuable moment may arrive late, when other parts of the mission have already used up attention, spares, and human energy, and if it fails, the failure has a particular cruelty. The crew may still be alive, the habitat may still hold pressure, and the surface may still be workable. But Earth has moved from destination to memory, and the practical access has changed even though the distance has not. That explains why the rocket waiting on Mars is more than engineering hardware. It is the boundary marker. As long as it can leave, the crew still has a reversible relationship with the planet. If it cannot leave, Mars has acquired them, and that shift in status does not require any announcement. A human Mars ascent vehicle has to lift people inside a pressurized volume, reaching the right orbit with the guidance and performance margin a rendezvous requires. Life support and docking capability come with it, and none of those can be optional. Mars helps in real ways. Its gravity is about 38% of Earth's, and its thin atmosphere means the velocity needed for orbit is lower than from Earth, which sounds generous and is genuinely helpful. But that advantage is smaller than the actual return problem makes it seem. Earth launch is surrounded by civilization. Roads bring hardware, cranes lift stages, and whole teams of engineers fill every gap in the background. On Mars, that background is missing. The crew has what was landed, what they brought, and what still works after the planet has had time to test it. Here is why the waiting matters. A Mars ascent vehicle may have to sit for months or years before use, waiting through dust and thermal cycling and low pressure. The surface keeps working on it the whole time. The hard question is not whether an engine can fire in a test stand. The hard question is whether the whole vehicle can remain a trustworthy exit after being part of a Mars surface system for a long time. We can test pieces on Earth, thermal chambers, vibration tables, and dust simulation against modeled conditions. Those tests are serious, and they are the reason any of this is thinkable. But the first crewed launch from Mars will still be the first crewed launch from Mars. The planet itself becomes part of the test environment, and the crew is already beyond ordinary rescue when that test arrives. Now look at timing. A vehicle used on day one has less time to age. A vehicle used near the end of a long surface stay has carried months of accumulated risk. The lifeboat must survive while other problems consume attention. It also has to be inspectable. If a crew cannot know the condition of the ascent vehicle, then the exit exists as faith, not as mission knowledge. Mars return needs health data, not only hope. The sample return analogy helps again. NASA describes a sequence where a small payload launches from Mars, reaches orbit, and is captured by another spacecraft. Launch is not the end, it is the doorway to the next link. For humans, that doorway carries people whose lives depend on the next vehicle being healthy too. A surface ascent that reaches the wrong orbit, misses the rendezvous, or consumes too much margin has not truly brought anyone home. So the ascent vehicle is both technical and emotional. It marks the boundary between a place that can still be left and a place that has become, for practical purposes, permanent. If the vehicle is healthy, Mars remains a destination with an exit. If it is compromised, the landscape does not change, but the crew's status does. That makes the vehicle more than a late-stage accessory, and it is the mechanical form of the promise. The round-trip claim sits inside its tanks and engines, its avionics, every system that has to fire correctly the one time it matters. Let's keep the claim bounded, and Mars ascent is not impossible, and lower gravity helps. Decades of rocket experience help. Robotic missions teach us how to land and operate machinery on Mars. But the evidence we need for human return is stronger than the evidence needed for confidence in a concept. It is the difference between saying a design can work and saying a crew may depend on it after the design has waited on another planet. That difference is where practical exile begins to become visible. Exile does not require a villain. It can begin with an exit system that looks plausible in the plan but has not been preserved in reality. The simplest inspection question becomes the hardest one. What has changed since landing? On Earth, a launch vehicle's condition is tracked minute by minute in a controlled campaign. On Mars, the answer has to include every change that temperature swings, dust exposure, and accumulated maintenance compromises have made across the whole surface stay. The vehicle is not judged against the day it was designed. It is judged against the day it must fly. And a rocket, no matter how well designed, cannot launch on intention alone, and it needs stored energy. It needs propellant. That is the next door in the chain. So the next link is obvious and unforgiving, and a rocket that waits beautifully but cannot be fueled is not an exit. It is a monument. So far, the way home has become more than a promise. It needs a real ascent vehicle kept alive on Mars until the crew can use it. The next question is what gives that vehicle the stored energy to leave, because a rocket without verified propellant is only the shape of an exit. So what does a way home need before it becomes real? It needs stored energy. It needs mass that can be thrown backward hard enough to lift people off another planet. A Mars return rocket is not only a vehicle, a propellant problem waits inside it. Many studied human Mars ascent concepts use liquid oxygen and methane. The details vary by architecture, but the basic reason is clear. Methane and oxygen can, in principle, connect to Martian resources in a way that hydrogen-heavy systems do not as cleanly. Now the scale matters. In a commonly cited MOXIE-linked analysis for a representative 6-person oxygen-methane Mars ascent vehicle, the total vehicle mass is about 50 tons, with roughly 31 tons of oxygen and about 9 tons of methane. That number can sound abstract, but 31 tons is not breathing oxygen for the cabin. Oxygen is rocket oxidizer, the chemical partner that lets fuel burn fast enough to push a vehicle into orbit, and oxygen dominates the mass. In that representative concept, oxygen is the largest single propellant burden by far, which means the question of return becomes partly a question of where the oxygen comes from. Let's compare the two broad paths. The first path is to bring the propellant, or most of it, from Earth. Earth knows how to make propellant and can fill tanks under controlled conditions, so that sounds simpler. But Mars punishes mass. Every kilogram that must arrive on the Martian surface has to be launched from Earth, carried across interplanetary space, and safely landed. The propellant for the way home becomes cargo for the way out. The second path is to make part of the propellant on Mars, and that sounds elegant. Mars has carbon dioxide in its atmosphere, and Mars has water ice in some regions. In principle, a local factory can reduce what Earth has to land, and yet local production changes the risk. It moves part of the return system into a machine that must work on Mars before the crew can trust the exit. So here is where we stand. We have established that return requires a rocket, and that the rocket requires propellant at a scale Mars does not simply hand over. The question that remains is whether Mars can help make the way home without turning the way home into a factory failure problem. Here is the first real locked door, and a Mars ascent vehicle can be designed beautifully on Earth. It can be landed ahead of the crew, and it can stand on the surface like a promise. But until the propellant story is solved, the promise is incomplete. The reason oxygen matters so much is not romantic. The problem is arithmetic. Rockets carry not only fuel but also the oxygen, or another oxidizer, that lets the fuel release energy where there is no air and no atmosphere to burn from. On Earth, we forget this because the launch pad hides the supply chain. Tanks are filled and vehicles are checked while ground systems handle everything else, so propellant simply appears as part of launch preparation. On Mars, there is no pad economy and no backup tanker can roll down a road. The mission has only what was landed and what it can produce, which means the way home becomes a stored chemistry problem. And this is why the next object is not another rocket. MOXIE is an experiment the size of a small appliance, bolted to a rover, quietly making oxygen from Martian air. The oxidizer point is worth holding for a moment, and in ordinary speech people say rocket fuel as if fuel is the whole story. In a vacuum, fuel alone is inert, and it needs something to react with, and oxygen becomes a return constraint. The oxygen is not there mainly because people breathe it. The rocket needs to carry its own fire. If all of that propellant is carried from Earth, the return system becomes front-loaded mass. If some is made on Mars, it becomes front-loaded industry, and neither path is free. One pays in launch and landing mass, the other pays in autonomous reliability on the surface. Now, propellant sounds like a storage problem, but it is really a mass problem. Every kilogram that has to be waiting on Mars must either be launched from Earth, landed through the Martian atmosphere, protected on the surface, or manufactured locally. There is no free path. Let's use the representative oxygen-methane ascent concept from the research as a scale anchor. One commonly cited 6-person Mars ascent analysis is about 50 tons total, with roughly 31 tons of oxygen and about 9 tons of methane. The exact design can change, and the lesson does not. Most of the propellant mass is oxygen. That sounds strange if we think of oxygen as the gas people breathe, and rocket oxygen is different in role. It is the oxidizer that lets fuel burn. In a methane oxygen engine, the methane is only part of the stored chemical energy system. The oxygen is the larger mass sitting beside it. So the return problem quietly becomes an oxygen problem. If all of that oxygen comes from Earth, the mission pays for it again and again. It pays at Earth launch. It pays during interplanetary transfer. It pays during Mars entry, descent and landing, where every extra ton makes the landing system larger and harder. That explains why local oxygen production is so attractive. Mars already has an atmosphere dominated by carbon dioxide. If a machine can pull oxygen atoms from that CO2, the planet itself supplies the largest propellant ingredient. But notice the trade. Importing propellant makes the landing mass brutal, while making propellant locally makes the return dependent on a working factory. Neither choice is magic, and each moves the risk to a different part of the chain. We should also keep the language clean. The oxygen for ascent is not the same topic as breathing oxygen in a habitat. A habitat may need oxygen systems, but this argument is about the mass that lets a rocket climb away. It is the difference between keeping people alive in a room and throwing a vehicle into orbit. Now imagine the crew looking at the ascent vehicle. The question is not, does the rocket exist? The question is, do the tanks contain verified propellant at the quantity and quality the mission requires? A nearly full tank may not be enough if the trajectory demands a specific margin. A full tank may not be enough if storage has contaminated something. A good production run may not be enough if the timing slips. So propellant is not a commodity in this story, it is the physical form of return capability. You can count it, you can test it, and you can lose it, and once we see that, the next question becomes sharper. If oxygen is the heavy part, and Mars offers carbon dioxide everywhere, how much of the escape system can the planet really provide? One commonly cited MOXIE-linked analysis gives the scale. For a representative 6-person oxygen-methane Mars ascent vehicle, the total ascent vehicle mass is about 50 tons, with roughly 31 tons of oxygen and 9 tons of methane. Those numbers are not a final mission design, they are a scale anchor. 31 tons of oxygen is not breathing gas for the cabin, but mostly rocket oxidizer, the chemical partner that lets methane release energy fast enough for ascent. Let's translate that. 31 tons is about the mass of several loaded city buses in oxygen alone, and none of that oxygen is for comfort. All of it is for leaving. That explains why the propellant question dominates the return promise. If all propellant is launched from Earth and landed on Mars, the mass problem grows sharply. Every kilogram that must land on Mars demands far more mass earlier in the launch chain. So mission planners look toward local resources, and the phrase is in situ resource utilization, often shortened to ISRU. Plainly, it means using what Mars provides instead of carrying everything from Earth. The idea is powerful. If oxygen is the largest share of the ascent propellant, and Mars has carbon dioxide in its atmosphere, then making oxygen on Mars could reduce how much has to be delivered from Earth. But notice what has happened, and the return problem has not disappeared. It has moved. Instead of carrying every kilogram of oxidizer, the mission now depends on an oxygen production system working on Mars before the crew needs it. Here is the first argument state bridge. We have established that return requires a real ascent vehicle, and that the vehicle needs propellant at a scale Mars does not hand over in tanks. The unresolved question is whether Mars can help make the way home. A propellant plan can follow several paths, and the mission can import more from Earth. It can make some on Mars, and it can combine imported feedstock with Martian material. Each choice moves the burden to a different part of the architecture. Importing propellant sounds conservative because it avoids relying on a Martian factory, but it is not simple. The propellant or feedstock has to survive transport, landing and storage, and it increases the mass that must be delivered safely to the surface. Producing propellant locally sounds elegant because it uses the planet, but elegance is not enough, because a factory that makes the way home has to be treated like part of the escape system, not like a science experiment beside it. Oxygen is the cleaner side of the story. Mars' atmosphere is mostly carbon dioxide, and a machine can split oxygen from that carbon dioxide if it has power and the right electrochemical hardware. That is the basis of the idea. Methane is less direct because methane needs hydrogen. That hydrogen can be imported from Earth or obtained from Martian water ice, if accessible resources exist where the mission can actually use them. So a simple phrase like "make fuel on Mars" expands into a chain of dependencies. It needs atmosphere intake and power. It needs processing hardware and storage. It needs verification before anyone boards. Every word hides a real machine, and every machine needs its own maintenance. The return promise depends on the verified quantity and quality of propellant, not on the concept that propellant could be made. A crew cannot launch on a press release. They launch on measured tanks, and the numbers in those tanks decide whether the exit is real. This matters because propellant is not optional mass. If the ascent vehicle is underfilled, contaminated, or leaking, the rest of the return chain may be irrelevant. So Mars return turns chemistry into trust. The question becomes not only whether propellant can be made, but whether it can be produced in sufficient quantity and stored at verified quality until the vehicle can use it. We should be careful here, and ISRU is not fantasy. It is one of the most serious ideas in human Mars planning. The reason it matters is that it could make otherwise enormous landed mass more manageable. But because it matters so much, it cannot be treated as magic. A mission that depends on Mars-made propellant has placed a factory inside the way home. We can see also a psychological trap in propellant numbers, and a percentage can sound close enough. 90% full feels reassuring in ordinary life. For a launch vehicle, the missing 10% may be the difference between reaching a safe orbit and entering the wrong one. Margins are not decoration. They are the part of the plan that absorbs reality when reality refuses to behave like the spreadsheet. And once the factory enters the chain, a new distinction appears, and proving a principle is not the same as trusting a lifeboat. That distinction is where Moxie becomes important, and that is where Moxie enters the story. Perseverance carried a small instrument called Moxie, and its job was simple to say and hard to do. It made oxygen from the carbon dioxide in the Martian atmosphere, and the mechanism was straightforward in principle. Moxie compressed that thin gas, heated a solid oxide system to around 800 degrees Celsius, and split molecules so oxygen could be collected. The result was measured in grams, not tons, and that distinction matters, and Moxie proved a principle on Mars. It did not fuel a return vehicle, and yet the principle is powerful. If oxygen is most of the propellant mass in a methane-oxygen ascent concept, then making oxygen locally attacks the heaviest part of the return burden. Here is the clean promise of ISRU, or in situ resource utilization, and the phrase means using resources where you are, instead of carrying everything from home. On Mars, it means turning the planet itself into part of the mission system. But here is the problem. The moment return depends on local production. The local production system becomes part of the lifeboat. A future oxygen plant would not be a science demonstration. It would have to land safely, deploy, and operate reliably for months or years through dust and temperature swings, without the benefit of an Earth support team nearby. It would have to produce enough oxygen at the right purity and feed that into storage the ascent vehicle can actually use. That sounds like a lot, and the scale is large, but the deeper issue is not the length of the checklist. The deeper issue is that every item on it becomes part of the way home. We should be careful here, and Moxie was a real achievement, and it showed oxygen production from Martian carbon dioxide under real Martian conditions. The chemistry is established science and engineering, not fantasy. What follows from this is more restrained. Scaling a gram-scale demonstration into a mission-critical plant for tens of tons of ascent propellant is a separate challenge. Moxie does not disprove the idea, and it does not solve the return problem either. It sharpens the question by showing the principle is real. Here is where Mars return becomes different from the heroic version of exploration. The heroic version says, we will go there and use local resources. The engineering version asks how many hours the plant must run without failure, and what happens if production stops at 80% of the required mass. The way home from Mars cannot depend on a hopeful reading of a gauge. It needs verified inventory with margin. It needs a way to know, before the crew boards, that the propellant is real. And this matters because Mars is not a laboratory next door. If a mission launches people before the oxygen inventory is confirmed, then those people are trusting a future event on another planet to preserve their freedom of return. Now look at the ethical shadow already forming, and a crew can consent to risk. Astronauts always have. But consent changes if the return path depends on a factory that has not yet completed its job. This does not mean local resources are a mistake, and they may be the only way to make human Mars return practical at scale, but they transform the problem. Instead of carrying every ton from Earth, the mission has to trust a small piece of industry on Mars. And oxygen is the cleaner half of the story. Methane points to a more complicated feedstock, because if oxygen can come from the air, the next question is where the rest of the propellant comes from. The scale-up problem is not only size, and the problem is duty cycle. A small instrument can run for demonstrations. A return plant has to run reliably, detect its own faults, and produce gas that downstream systems can trust. All of that on command. That asks for a different category of confidence. We can see the trade clearly, and ISRU is attractive because Mars gives one feedstock everywhere, carbon dioxide. But a feedstock is not a system. The feedstock has to pass through machinery, thermal control, and storage, and every valve and sensor has to behave the way the software expects, under conditions no laboratory can fully replicate. Each part becomes part of the exit chain. Now MOXIE is easy to oversell, and that would be a mistake. The instrument did something genuinely important. It made oxygen on Mars from the Martian atmosphere, and that actually happened. But MOXIE was a proof of principle, not a finished escape system. It produced oxygen at experimental scale, and future return architectures would need production at a much larger rate, over a longer period, with storage and verification tied to a crewed ascent vehicle. Let's walk through the mechanism without turning it into a chemistry lecture. Mars air is mostly carbon dioxide. MOXIE compressed that thin air, heated a solid oxide electrolysis system to very high temperature, and split oxygen atoms away from carbon monoxide. The important point is not the appliance. The important point is that Mars' atmosphere can become usable oxygen. Here is a real threshold, and before MOXIE, local oxygen production on Mars was a studied idea. After MOXIE, it was a demonstrated process on another planet, and the gap between those two states is genuinely important, and yet the gap after MOXIE matters just as much. A mission-critical plant has to run when commanded and keep running through dust and temperature swings. It has to produce enough oxygen at the right purity, then move it into storage the ascent system can use, so the lifeboat becomes a small industrial chain. Intake leads to electrolysis, then to cooling and storage. Each step is understandable by itself, and together they become the thing the crew trusts instead of a rescue ship. Here is the trap, and a small demonstration can be successful and still leave the main question open. That is not an insult to the demonstration, and it is the normal path of engineering. Airplanes did not become airliners after the first controlled flight, and nuclear power did not become a grid because one reactor achieved criticality. A principle has to become an operational system, and that journey takes time and proof. We need that same patience here. MOXIE tells us Mars can help, but it does not tell us a crew can bet their return on a scaled oxygen factory without proving every reliability step in between. Now think about where this plant sits in the mission. If it runs before the crew arrives, then Earth operators may have to verify from a distance that the oxygen inventory is ready. If it runs while the crew is present, then the crew may be able to service it. But the mission has accepted a dependency that matures after people are already committed. Those are not identical risks. Pre-production can make the mission safer by refusing to launch crew until the return stockpile exists. Surface production can reduce pre-positioning mass, but it may ask the crew to live beside an unfinished exit. So the clean statement is this: MOXIE made the return chain more plausible. It did not make the return chain automatic. The output was small, gram-scale oxygen, enough to prove the process under Martian conditions, but not enough to fill a human return rocket. That distinction carries the whole argument. MOXIE proved the principle. A return architecture would need mission-scale production and verified reliability. That is a different category of proof. A future oxygen plant would have to produce at kilogram per hour scale, not gram scale. It would have to operate for long durations and survive dust, thermal cycles, and the ordinary awkwardness of machinery far from repair shops. So MOXIE does not make Mars return easy. It makes the return problem clearer. If oxygen is most of the ascent propellant mass, then oxygen production becomes one of the major gates between a plan and a real exit. Let's slow down on that, and a small experiment can be allowed to fail gracefully. It can return partial data, and it can run when conditions are favorable. A lifeboat factory cannot be treated that way. If a return plan depends on oxygen ISRU, the oxygen plant has to work before the crew needs to leave. It has to make enough oxygen and make it pure enough, then place that oxygen into a usable state for the ascent system. Then the product must be stored. Oxygen for rocket propulsion is often cryogenic, so keeping it in the right condition over time becomes a system in itself, requiring insulated tanks and active boil-off management that must hold over months. Each of those pieces can be engineered, and none is supernatural. But the chain has to be counted honestly, because the crew's way home can be weakened by any link that remains only partly proven. Here is why the word factory is useful. It stops us from imagining ISRU as a single box that says fuel. A factory has intake and processing, thermal management and output monitoring, and each step requires maintenance the mission has to plan for. On Earth, factories are surrounded by people and supply chains. On Mars, a mission-critical oxygen plant may have to be factory, technician, and warning system all in one. The moment oxygen production becomes part of the exit, its failure mode changes, and it is no longer only a lost opportunity to save mass. It can become a direct threat to the credibility of return. That does not mean the better answer is always to carry everything from Earth, and carrying everything has its own penalties. Mass from Earth is expensive, hard to land, and unforgiving at scale. The honest answer is that every architecture pays somewhere, and ISRU pays in autonomous reliability. Imported propellant pays in launch and landing mass. Hybrid approaches pay in both, but sometimes less severely. For the viewer, the important point is not which trade wins in a specific mission design. The point is that the way home must include the trade explicitly. A Mars crew should not be asked to trust a phrase like local resources. They need a measured status, how much oxygen exists, whether it is usable, and what margin remains if something goes wrong. Moxie gives us a clean boundary between evidence and hope, and evidence says oxygen can be made from Martian carbon dioxide at experimental scale. Hope says the scaled plant will be ready when needed. Engineering is the hard work between those two sentences. Here is where a mature program would be humble, and it would celebrate the demonstration and then immediately ask the colder questions. How long can the scaled plant run without human repair? What fails first and under which conditions? The answers do not make the achievement smaller, they make it usable. And oxygen is the easier side of the local resource story, because it comes from the atmosphere that surrounds every landing site. The methane side points to a resource that may not be in the right place at all, and oxygen is only the cleaner half of the propellant story. Methane pulls us toward water, hydrogen, and a harder geography problem. The phrase Mars Fuel Factory can make the problem sound finished, and Mars has carbon dioxide. Bring the right machine, make propellant, and come home. But oxygen is only part of the return story, because methane also needs hydrogen, and hydrogen has to come from somewhere. One option is to bring hydrogen from Earth. That keeps part of the chemistry under Earth control, but it does not remove the transport problem. The hydrogen still has to survive the journey out and long-term storage on the surface before it can be used. Another option is to obtain hydrogen from Martian water or ice, and that sounds more self-sufficient. But it introduces a new chain: find the water and reach it, mine and process it into a usable form, and keep all the equipment alive while doing it. Each step in that chain is a machine with failure modes. Let's slow down here. Water on Mars is not the same as water at the place a crew needs it, in the form a machine can use it, at the time the ascent vehicle needs propellant. That distinction is everything, and a map can show ice. A mission needs accessible feedstock. The difference between those two things can decide whether local methane production is a practical part of the way home. Landing sites become harder under this logic. The best site for water may not be the best site for safe landing, and it may not suit the terrain or sunlight conditions that crew operations require. That is before human operational needs enter the picture at all. So the return chain reaches backward into site selection, shaping the mission before the crew has ever seen the surface. Before the crew arrives, planners are already asking whether the landscape can support the exit system, and Mars is no longer only the destination. It becomes the supply side of the route back. And here again, the danger is not that any one problem is impossible. The danger is that the return promise collects dependencies quietly, each one manageable alone, harder together. A single dependency can be managed, but many dependencies begin to interact in ways that compound. If the water site is far away, transport becomes a real operational burden. Vehicles, maintenance schedules, and crew time all follow from that single site distance fact. and all of it leans back eventually on the ascent vehicle. We have to keep the lane narrow, and we are not telling a general water on Mars story. We are not asking how to build farms or cities, but whether the crew's return propellant can be produced, verified, and trusted. That question is sharper than it first appears, because a return plan that depends on local methane is not just saying Mars has resources. The claim says a specific chain of machines can turn those resources into a departure capability before the crew runs out of time. Now imagine the propellant plant reaches full inventory with oxygen present and methane present. The ascent vehicle is ready, and the crew has an exit system on the surface. They still cannot leave whenever they want. Mars is moving and Earth is moving, and the two planets are not connected by a permanent road. The route home opens and closes according to orbital geometry, and that is the next locked door. Even a fully fueled rocket does not create a good trajectory by itself. The rocket and the planets have to agree on the same moment. There is also a geographical tension underneath all of this. Mission planners do not choose a landing site for one reason. They have to weigh terrain, sunlight, and thermal range together, and adding a water extraction requirement for return propellant forces the site to satisfy yet another demanding condition. Mars may offer resources, but not necessarily where the whole mission wants to live. Here is where local resources stop being a slogan and become logistics, and ice in the ground does not flow into a tank. It has to be accessed by machines that can work in Martian soil, and those machines need power, maintenance, and time. If they fall behind, the return chain falls behind with them. Now, methane changes the mood of the argument. Oxygen can be pulled from the air almost anywhere on Mars, at least in principle. Methane usually points to hydrogen. Hydrogen points either back to Earth or down into Martian water. Here is the fork. Bring hydrogen with you, and you have preserved an Earth-supplied dependency. Find water on Mars, and you have created a mining dependency instead. Neither is absurd, and neither is free. Let's keep the chemistry at the right altitude. Carbon dioxide plus hydrogen can be turned into methane and water through processes often discussed in Mars ISRU studies. The exact plant design can vary, and the practical issue is feedstock. If the hydrogen is not already there, something has to provide it. Water ice looks like the elegant answer because Mars has native water resources. But water in a paper is not the same as water at the landing site. It may be buried, mixed with soil, or far from the best place to land a large vehicle and keep crew operations running. So the return chain begins to shape geography, and the best site for science may not be the best site for propellant. The best site for water may not be the safest site for landing. Mars does not arrange its resources around the convenience of a crewed ascent vehicle, and that creates a second problem. Mining is not just finding, it is access. A mission that depends on water must dig, heat, and purify material. Each verb is a machine with mass and failure modes, and each machine needs power and maintenance. We can see why this does not belong in a general Mars survival episode. Water for drinking and water for agriculture are important, but they are not the claim here. Here, water matters because it may become methane, and methane matters because it may become the return burn. Now imagine two mission designs side by side. In the first, methane or hydrogen comes from Earth and lands before the crew. That is heavier on the outbound leg, but the feedstock is known and controlled. In the second, the mission makes methane from Martian resources, cutting the landing mass but adding a factory dependency on the surface. The return chain has not disappeared in either case, it has changed address. Here is a recurring pattern in Mars architecture, and a solution to one constraint often becomes a dependency somewhere else. Local resources reduce the transport burden but increase what the surface operation has to prove. Imported supplies reduce local complexity but drive up launch and landing mass in ways that compound at every step. So the correct question is not which option sounds futuristic. The correct question is which chain can be verified before human lives depend on it. And even if the propellant problem is solved, the crew still cannot leave whenever fear, illness, or failure says they should. Another path is to use Martian water ice. Water contains hydrogen, and if water can be found, extracted, and processed into a usable form, it can help close the methane side of the propellant story. The phrase "if water can be found" sounds gentle. It is not gentle in mission design. It means the return chain may depend on geology and landing site selection, on drilling and filtration equipment that all have to function reliably. That is a mining operation, not a tap. Mars has water ice, and that is established, but useful resource is not the same as known existence. Useful means accessible, concentrated enough, and close enough to be compatible with the rest of the mission. This creates a site choice tension that shapes the mission before anyone lifts off from Earth. The best place for ice may not be the best place for landing, and it may not suit the solar power levels or thermal conditions that crew operations require. The resource and the mission rarely want the same ground, and the architecture has to decide which constraint wins, so the return system can begin shaping the entire mission before anyone arrives. If methane production needs local water, the map of Mars becomes a map of possible exits. Let's keep this within the lane. Water matters here because hydrogen can become part of the route home, not because of farms, lakes, or terraforming. If the hydrogen is imported, the mission carries a transport dependency from Earth. If it comes from Mars, the mission carries a mining and processing dependency on the surface. Both routes need proof, and neither one is simple. The storage problem returns as well. Methane and oxygen have to be kept in conditions the ascent vehicle can actually use, because making propellant is not enough if it cannot be stored and loaded when needed. A surface factory also needs power, and power systems have their own failure modes, and dust can reduce solar output. Nuclear systems have different mass and safety considerations. Backup power adds mass and complexity. Here is how a clean chemical idea turns into mission architecture, and a reaction on paper becomes machinery on the ground. Machinery on the ground becomes maintenance. Maintenance becomes crew time and monitoring and difficult rules for what happens when output falls behind schedule. The return clock keeps running during all of this. The launch window will not wait because a pump is underperforming or a drill reached poor quality ice. Orbital mechanics does not negotiate with production delays. Here is one reason a weak propellant architecture can quietly turn a two-way mission into a long wait. Not because anyone declared one-way settlement, because the resource chain did not mature into a verified exit before the calendar arrived. We should not imply that water extraction is impossible. It may be solvable. Robotic prospecting, careful site selection, and engineering demonstrations can reduce risk, and conservative margins help further, but the standard is high because the consequence is high. If local methane production is part of return, then water access is not a convenience, it is one of the foundations of crew agency. The viewer can now see the locked door pattern, and the rocket needs propellant, and the propellant may need a factory. The factory may need water, and the water may effectively choose the landing site before the crew ever sees Mars. Power ties this whole resource problem together. Every step in a local propellant chain, from extraction and purification to chemical conversion, requires energy, and cryogenic storage requires it continuously. If a dust season reduces solar output or a nuclear unit loses capacity, propellant production can slow at exactly the wrong time. A resource is only useful when the mission also has the energy and machinery to turn it into departure mass. And even if every tank is full, another gate remains, and Mars and Earth have to be in the right positions. The crew may be ready, and the rocket may be ready, but the sky may not be. For that, Mars makes everyone wait. By now, the exit has become physical. A vehicle, an oxygen system, and a resource chain that all have to survive contact with Mars. What remains unresolved is whether those pieces are ready at the moment the planets allow a return, because Mars does not wait for the architecture to catch up. On Earth, an emergency changes the schedule. On Mars, an emergency may only change the urgency, because the planets still move the way they move, and a crew cannot demand a return path from the sky. Let's use the simplest version of the idea, and a spacecraft does not fly to where Mars is when it launches. It flies to where Mars will be when the spacecraft arrives, and the same logic applies in reverse. Leaving Mars means aiming for where Earth will be after months of travel. So launch windows matter. NASA and JPL Public Material explain the basic cadence clearly. Favorable Earth-Mars opportunities for efficient conventional transfers recur roughly every 26 months, and the useful windows last only weeks. 26 months sounds like a schedule. On Mars, it can become a wall. A representative long-stay Mars mission often involves months outbound, a long surface stay, and months back. Exact numbers vary, and the important point is not one fixed architecture. The important point is that low-energy return is tied to planetary alignment. So if something goes wrong halfway between return opportunities, the crew may not be able to leave in the ordinary sense. They may preserve options and prepare resources, but the sky may not offer a practical departure path yet. This changes the meaning of evacuation. On the International Space Station, evacuation can mean a vehicle returning to Earth in hours. On Mars, evacuation may mean surviving until the next return window opens, then launching to orbit, completing the rendezvous, and spending months crossing interplanetary space. And all of that assumes the full return chain is still intact, while the crew is managing whatever problem forced the departure in the first place. The crew may choose the mission, they may not freely choose the day they come home. That sentence is the heart of the calendar problem, and the problem is not fear. The problem is geometry. Now, future propulsion could change parts of this picture. Higher energy transfers, different vehicle architectures, or advanced systems could widen options. But widening options is not the same as removing the constraint. Under current and near-term planning, Mars return timing is still governed by orbital mechanics. So here is where we stand. The way home needs a rocket, propellant, and a celestial calendar that opens at the right time. The unresolved issue is whether the crew can connect all of that to the vehicle that actually brings them back toward Earth. Because leaving the surface is only the beginning of return, and a Mars ascent vehicle does not usually bring the crew all the way home, it gets them to the next handoff. And that handoff happens in Mars orbit, where timing and precision matter again. The surface rocket is the first escape, and the orbital return vehicle is the second. Between them is a rendezvous that has to work. The calendar also affects psychology. A crew living on Mars would know that some days are closer to possible departure than others. The planet can feel open when the window approaches and sealed when it has passed. That pattern is not drama. Orbital mechanics does this to human planning automatically. And it makes emergency planning strange. A failure that would trigger evacuation in Earth orbit may trigger conservation on Mars. The mission may have to change from go home now to stay alive until going home is possible, and that shift is one of the deepest differences between Mars and every human spaceflight environment we have used so far. Now, launch windows are often explained as a scheduling inconvenience, and for a Mars crew they are more than that. They decide when the way home is physically efficient enough to use. Let's start with the intuition. On Earth, emergency travel feels immediate. A helicopter can lift, a ship can sail, and an aircraft can be diverted. The response may be difficult, but the calendar does not usually forbid the route. Mars is different because planets move, and you do not depart toward where Earth appears in the sky. You depart onto a path that meets Earth later, after both worlds have continued around the Sun. That geometry creates favorable windows, and those windows recur roughly every 26 months. 26 months is not a planning number in the administrative sense. It is more than 2 years, and a crew that misses one favorable return opportunity may be facing an entirely different medical, technical, and psychological reality before the next one. That does not mean every possible trajectory disappears between windows, and higher energy paths can exist. Different propulsion can change the trade space, but cheap and practical routes are not available on command. The price of leaving at the wrong time can be enormous propellant, longer exposure, or unexpected mission risk, so evacuation becomes a strange word. On Earth, evacuation means moving people out. On Mars, evacuation may mean stabilizing the problem and surviving until the window opens, then launching to orbit, meeting the return vehicle and spending months in transit. The action is the same word, the scale is not. We should let that sit for a moment. An emergency can happen today, the best departure may not. Here is one of the deepest differences between Mars and every difficult environment on Earth. Antarctica is isolated, but aircraft can eventually come, and submarines are dangerous, but rescue concepts exist within a terrestrial system. Mars lives under celestial timing. The planets do not negotiate with mission control. Now this calendar also affects the ascent vehicle and propellant. And it is not enough for the rocket to be ready in a general sense. It has to be ready when the window opens. If production finishes late, if an inspection reveals a problem, if a medical issue changes the crew's tolerance, the geometry does not pause, and because the window lasts weeks rather than years, delays can become structural. A small slip near the wrong time can turn into a long stay. A long stay consumes supplies and stresses equipment. It changes bodies, and it increases the chance that some other link will weaken. So the calendar is not a background fact, and it is a member of the crew. It sits inside every contingency plan. Here is why the phrase, "they can always come home," has to be treated carefully. They may be able to come home when the return chain and the sky agree. Those are not the same sentence. NASA and JPL explain this through launch windows. Favorable opportunities recur roughly every 26 months, and the best window may last only weeks. Miss it, and under conventional transfer planning, the wait can be close to 2 years. That fact changes the meaning of evacuation. And on Mars, leaving is not only a decision, it is an alignment between vehicle readiness, crew condition, and the planetary geometry that only opens on its own schedule. Let's make the geometry plain, and Earth moves around the Sun, and Mars moves too, on a wider orbit and at a different speed. A spacecraft leaving Mars has to meet Earth, where Earth will be months later. So the crew may choose the mission, but they do not freely choose the day they come home. Physics has a calendar, and the calendar is indifferent to human urgency. Representative human Mars mission studies often use long transits and long surface stays. The numbers vary, but the familiar conjunction class pattern is months outbound, hundreds of days on Mars, and months returning. The important number is not exact duration. The important idea is lock-in. Once the crew is on Mars, the return date is not a casual scheduling choice. If a major system fails halfway between favorable departures, the mission cannot automatically convert into an immediate Earth return. It may need to stabilize the situation and wait for the next window, or accept a much more demanding trajectory if one is available under its architecture at all. Here is where the return chain becomes more severe than a normal rescue plan. Rescue on Earth means outside capacity arrives. Rescue on Mars often means the crew must use the pre-existing exit chain at the pre-existing celestial moment. There may be emergency options in some designs. Extra propellant reserves, abort trajectories, and alternative orbital stays can be engineered in. But every emergency option has mass and complexity, and mass and complexity were already the problem. The point is not pessimism, and it is accounting, and if the architecture claims early return, the architecture has to pay for early return. If it does not pay, then early return is not a real option. Here is the second argument state bridge, and we have a rocket, propellant, and now a celestial calendar. The way home is no longer a vehicle alone. It is a vehicle becoming ready at the same time the sky becomes usable. That explains why a delay in propellant production is not merely local, and it can push against the launch window. A small delay can become a long stay if it crosses the wrong boundary. The same is true for crew health. A medical problem does not become less serious because Mars and Earth are poorly aligned. It becomes harder to act on because the route home may be closed or expensive. At this distance, time is not a background variable. time is one of the materials of the return architecture. The mission has to carry enough of it, protect enough of it, and know what happens when it runs short. The moon is sometimes mentioned in these conversations, but only one contrast matters here, and the moon can be treated as a nearby emergency environment in ways Mars cannot. Mars lives on a different rescue clock, and no terrestrial analogy fully captures that difference. The window also creates a communication problem with the public, because to people on Earth, a delay can sound like ordinary schedule slip. On Mars, a delay near departure can carry the weight of an extra season, an extra year, or an extra conjunction cycle. The language of project management becomes inadequate because a missed date is not always a missed date. Sometimes it is a changed mission. So when the window opens, the crew is still not home. They have only reached the moment when the next link can be attempted, and the rocket must leave the surface and find the rest of the way back in Mars orbit. And once the window does open, leaving the surface is still not enough. The crew has to meet the next piece of the way home. When the ascent vehicle leaves Mars, the crew is not home, and they are not even on the path to Earth yet. They are trying to reach the next link. Here is where the Mars sample return analogy becomes useful again. Even a small sample container needs a chain. Launch it from Mars, find it in orbit with another spacecraft, and send it back to Earth. The surface departure is only one step. For humans, the architecture is larger and the stakes are different. But the lesson is the same. Surface to orbit is not return, and the exit is a handoff. Let's picture the human version. The crew boards the ascent vehicle. It launches from Mars and inserts into a target orbit. Then it has to meet a return habitat or Earth return vehicle. The crew transfers, and the return vehicle performs the burn that sends them home. Every word in that sequence is doing work, and none of them are decorative. A small error can become large when rescue is not nearby. The ascent trajectory has to be accurate enough, docking has to succeed, and life support margins have to cover the whole operation without assuming anything will be easy. And the crew performing this has already lived through the outbound transit and the surface stay. They are not fresh pilots stepping into a simulation bay. They are people who have spent a long time away from Earth. Here is why the phrase coming home can be misleading, and it sounds like a direction. In practice, it is choreography. The choreography may be planned beautifully, and it may have redundancy, and it may use proven rendezvous principles from decades of orbital operations. Those facts matter. Human spaceflight knows how to rendezvous and dock in Earth orbit, but Mars orbit is not Earth orbit, and the support environment is different, and the consequences of a failed handoff are different. The timeline for help is different. So the return chain is not fragile because engineers are careless. The sequence is fragile because many correct things must remain correct, far from the infrastructure that normally absorbs mistakes. Now think back to the rocket on the surface, and at first it looked like the way home. By this point it has changed, and the ascent vehicle is not the whole exit. The ascent vehicle is only the first vehicle in a chain of vehicles. That change matters, and a crew can leave the surface and still not have solved the return. They must reach the orbit where another promise is waiting. And if that promise is kept, the surface story appears to end, and Mars falls away. The return burn begins, and Earth is no longer only a point of light. The exit becomes a trajectory. But the biological story does not end. The people inside the vehicle still have to come home, and their machines may be on the right path while their bodies are not back yet. Rendezvous is one of the great achievements of human spaceflight, and the choreography is not new magic. Every human orbital program has depended on the ability to meet in orbit, and decades of practice have made the skill real and repeatable. But the Mars version removes the comfort of nearby infrastructure. The same skill is now being applied where the fallback options are fundamentally thinner. The handoff also introduces role separation, and the ascent vehicle may be optimized for getting off Mars. The return vehicle may be optimized for months in deep space. The crew has to move from one to the other without treating either as the whole answer. Efficient architecture creates a seam, and seams are where systems have to be most honest. One useful way to see the handoff is to separate navigation from access. Navigation asks whether two vehicles can reach the same place at the same time, while access asks whether the crew can actually move through that meeting point and continue toward Earth. Those are not identical questions. A return vehicle may be in the planned orbit and still be unavailable if docking hardware has a fault. The ascent vehicle may arrive close enough for normal operations and still be in trouble if consumables are tighter than expected. A crew may complete the launch and still face the hardest minutes of the day after the engine has shut down. So the proof standard has to include the seam itself, and not just the ascent burn, not just the parked return vehicle. The proof has to show the whole transition, approach, capture, and transfer into the Earth return burn. Even the word capture deserves respect. For a sample container, capture can mean a spacecraft finding a sealed object and enclosing it. For people, capture means docking two life-supporting machines with no nearby rescue vehicle and no ground crew able to touch the hardware. The physics may be familiar, but the operational meaning is not. A clean handoff also protects time. If the orbital transfer takes longer than planned, the return vehicle may spend propellant, power, or crew margin that was meant for the trip home. Small losses can follow the crew into the next phase, and the chain does not reset when the hatch closes, so Mars orbit becomes a kind of checkpoint. The mission can have left the surface and still be proving whether the return architecture is real. Now, orbit sounds like safety because it means the crew has left the surface, and in reality, Mars orbit is only the next room in the maze. The crew is no longer trapped on the ground, but they are not home. Let's picture the handoff. The ascent vehicle launches from Mars and climbs through thin atmosphere into the planned orbit. Somewhere else, a return vehicle or transfer stage has to be in the right orbit, fully powered, and healthy enough to receive the crew and begin the next phase. Here is the difference between escape and return, and escape means leaving the surface. Return means connecting with the system that can cross interplanetary space. NASA's sample return architecture makes this visible at small scale, and a sample container does not simply leap from Mars to Earth. It has to be launched into orbit, found and captured by another spacecraft, and then sent onward. For humans, the stakes are categorically different. The payload is alive, and the timeline is medically bounded, and a missed handoff is not a mission failure but a human emergency. So rendezvous is not a technical footnote, and it is the moment when two separate histories must meet. One vehicle has waited on the surface, and another has waited in space. Their orbits, clocks, and guidance systems have to agree. Now compare that with docking near Earth, and low Earth orbit is hard. But Earth is close, tracking is dense, and abort options are richer. Mars orbit removes most of that comfort, and light time delay means Earth cannot fly the event in a hands-on way. The vehicles and crew need autonomy, and autonomy is not only software, it is training and fault detection and crew judgment under stress. If the ascent trajectory is slightly off, or if a hatch or pressure seal does not cooperate, the solution has to exist there, not in a room back on Earth that can only advise after the fact. We can see the chain tightening, and propellant made departure possible, and the window made departure useful. Rendezvous makes departure meaningful, and that is also where the architecture is most exposed. Here is the uncomfortable part. A successful launch can still fail the return if it cannot connect. That is why the Mars ascent vehicle cannot be designed as a heroic standalone rocket. It is a component in a choreography. The return vehicle has its own weighting problem. It may have been launched earlier and spent a long period coasting, orbiting and managing power and thermal control before the crew arrives. It too has to remain real. So Mars orbit becomes a test of integration, not integration as a bureaucratic word, but as a physical event where one fragile chain segment hands living people to the next. Mars sample return again offers a useful picture. A small sample container would launch from Mars, enter orbit, and then be captured by another spacecraft that carries it back toward Earth. For humans, the design is different and much larger. and the principle is the same. The surface vehicle and the return vehicle have to meet. Rendezvous is not magic. It is orbital geometry and propulsion, with navigation and docking hardware and crew procedure all working together. On Earth orbit missions, rendezvous has become routine in the sense that experts know how to do it. Routine does not mean casual. It means a difficult operation has been practiced inside a support system. Mars orbit does not offer the same background support, and the timing is delayed, and the vehicles are far away. The crew may be deconditioned, and the ascent vehicle may have limited life support margin. The return vehicle must be exactly where the chain requires it. So the handoff is a narrow place in the architecture, and the crew is no longer on the surface. They are not yet on the long road to Earth. They are in between, and that middle place is where the chain is most exposed. A small error can matter more than it would anywhere else. The wrong orbit costs propellant the return vehicle may need. A delayed docking consumes consumables. A sick crew member changes the tempo, and all of that has to be absorbed without a ground team nearby. The point is not an operational thriller, and we do not need to dramatize it. The choreography is serious enough on its own, and the physics does not require embellishment. The handoff also shows why the phrase return vehicle can mislead. There may be more than one. A surface ascent craft hands off to an orbital stage which connects to the Earth entry system. The name home is spread across hardware. Integration again becomes the quiet ruler. The ascent vehicle must reach the right orbit, the docking system must match, and crew procedures must account for suit state, physical condition, and time margins that shrink each time something does not go exactly as planned. A return chain can fail at the boundary between systems, even if each system looks sound alone. Interfaces are where optimism often hides. Let's bring the viewer back to the central object, and the rocket waiting on Mars was never the whole way home. It was the first moving link after surface life ended, and its job is to deliver the crew to a second promise. If that second promise is not ready, ascent becomes a dangerous halfway act. The crew has left Mars, but Earth is still only a plan. Here is why human Mars return planning cannot be judged by asking whether any single piece is plausible. The pieces have to meet its speed in orbit at the right moment, with people inside them. The handoff also has an emotional asymmetry. Leaving the surface may feel like escape, but the crew has entered a period where failure modes are less visible to ordinary imagination. A habitat leak is easy to picture. A rendezvous geometry problem is not. Yet for the crew, the invisible orbital details may be just as decisive as the visible rocket plume that lifted them away from Mars. And if the crew reaches the return vehicle, the surface problem is over, and the human problem is not. The body that boards the vehicle is not the same body that left Earth. And if the handoff works, the crew has solved only one category of distance, and the planet is behind them. Earth is still months away. A successful departure from Mars solves the mechanical problem of leaving the surface. It does not solve the human problem of returning to Earth. Home is a gravity field, and the return vehicle is a medical environment, and a human body has to function again under conditions it has not felt for years. NASA's Human Research Program has catalogued the broad hazards of deep spaceflight. For this video, we only need the part that touches return. The sequence is unusual. A Mars crew may spend months in microgravity during the outbound trip, then live for a long time in Mars gravity at about 38% of Earth's, and then spend months again in microgravity on the way back. That pattern is not a pattern humans have tested at full scale, and we have long-duration microgravity data from space stations. We have brief lunar surface experience. We do not have years of real human data from Mars gravity, so the honest position is restrained, and we cannot say a crew could not recover. We also cannot pretend the full extent of the recovery problem is already understood. The return question is narrower than a general health survey. What condition is the crew in when the chain asks them to perform? Muscle, bone, and cardiovascular function all matter here, but only as they bear on the specific demands of ascent, transit, and Earth re-entry. They may need to board the ascent vehicle and tolerate launch loads, then operate through rendezvous, then endure months of return transit. Then they must re-enter Earth gravity and survive recovery. Think about that last step. Earth is the destination, but Earth gravity is also a stressor, and a body adapted to months away from 1G does not become normal because the capsule crosses the atmosphere. Here is why the phrase home is complicated. Earth may be medically safer than Mars, but the act of returning to Earth can still be physiologically demanding in its own right. And this feeds back into mission architecture. A return plan is not credible if it only tracks vehicles. It also has to track the human condition of the crew at the time those vehicles must be used. The problem becomes sharper if the mission is delayed, because any extension, whether a missed window or a propellant shortfall, means more time adapting to Martian conditions and more cumulative radiation exposure before the crew has to perform. The biological clock keeps running while the exit clock waits, and the two do not coordinate. None of this proves doom, it proves coupling. Mechanical return and biological return are coupled systems, and the crew's body is part of the chain, not cargo that can be ignored until landing. And the next question follows naturally. If the body becomes the limiting factor, what kind of medical help is actually available? On Mars, the answer is not the answer we are used to. Partial gravity is the great missing gap in human data. We know a great deal about microgravity compared with what we once knew, but we know far less about whether Mars gravity is enough to preserve the body in the ways a return mission needs. 38% of Earth gravity may help, and it may not help enough, and the honest answer is that we have not yet lived the experiment. The body also accumulates experience. Radiation exposure does not reset because the return window opens, and isolation does not vanish because the vehicle is fueled. Sleep debt and immune changes can affect performance, and for return architecture, readaptation becomes part of operations rather than an afterthought. Now it is tempting to treat the human body as cargo once the vehicles work. That is not right. The body is part of the return system. It has to tolerate ascent and re-entry and Earth gravity after a long period away from all of them. Let's start with gravity, and Mars has about 38% of Earth's gravity, and that is more than the Moon, but it is not Earth. We do not yet have long human data for living in Mars gravity. We know microgravity changes muscle, bone, and cardiovascular function. We do not know exactly how years in partial gravity will translate when someone returns to 1G. 1G sounds ordinary because we live inside it, but after a long mission it may not feel ordinary. Standing, walking, and maintaining blood pressure can all become part of the endgame, and tolerating re-entry loads adds further strain on top. Radiation adds a different kind of uncertainty. The crew has spent months outbound, months or years under partial protection on Mars, and months inbound. The risk does not create a single dramatic moment. It accumulates. It changes lifetime cancer risk, immune stress, and possibly acute mission decisions if a solar particle event or medical condition intersects the timeline. So coming home is not over when Earth appears, because the body still has to be received by Earth. That phrase matters. Earth is home, but Earth is also a planet with full gravity and dense atmosphere. The crew may arrive depleted, needing immediate medical support and rehabilitation, with their bodies not yet able to handle ordinary stresses normally. We should not exaggerate this into helplessness. Astronauts return from long stays in orbit and recover, with countermeasures and medical monitoring as central parts of modern spaceflight. The point is not that the body cannot come back. The point is that return architecture has to include the body honestly, from ascent through recovery. Now consider how this feeds backward into Mars departure. A crew member who is medically borderline may change ascent risk, and a mobility issue may complicate suit operations or docking. The human body is not outside the engineering chain, it is load-bearing within it, and this is where Mars differs again from low Earth orbit, and from the space station. Return can be hours away once a departure begins. From Mars, return is still a long mission after departure, and there is no quick ride to a hospital. The medical system has to travel with the crew, so the body is both passenger and constraint. It determines what accelerations are acceptable, what workload the crew can perform, and what failures can be tolerated during the final sequence. When people say bring them home, they usually imagine the emotional moment and a capsule descends. A hatch opens and families wait. But the scientific question is harsher. What condition are they in when the hatch opens, and how much of that condition was shaped by the return chain long before Earth was visible? Gravity is the cleanest example, and we have long-duration human data from microgravity in Earth orbit. We have short lunar experience from Apollo. We do not have years of human life in Mars gravity, followed by return to Earth. And that is not a claim that Mars gravity will ruin the body. It is an uncertainty. The honest position is that long-duration partial gravity remains one of the unresolved biological facts in the return chain. The body's physical reserves all matter differently when a person has to launch from a planet, endure months of transit, and then re-enter Earth gravity. Immune response and cognition are part of that picture too. A crew might be medically stable on Mars and still face a difficult return. Stability inside a surface habitat is not the same as readiness for ascent and the full demands of Earth re-entry. Radiation belongs here in the same limited way, not as the headline hazard, but as a factor in mission duration. The question is whether cumulative exposure across outbound transit, surface stay and return transit remains within medically acceptable bounds. Distance also changes medicine in a structural way. On Earth, a medical problem can be handed to a larger system, and in low Earth orbit, evacuation and near real-time consultation are still part of the background. Mars removes that background entirely, and that removal forces a different kind of self-reliance. Before we reach medical autonomy, pause on readaptation. Returning to Earth is not simply arrival at a safe place, because crews after long spaceflight can require assistance and rehabilitation before normal function returns, and a Mars crew may come back after a much more complex exposure sequence. The re-entry and landing system has to account for people who may not be operating at ordinary physical capacity after all of that. That changes the design of the final link, and the return chain includes not only the capsule or vehicle that reaches Earth, it includes the support needed immediately after landing. Here the title gains another layer. Coming home is harder not because Earth is hostile, but because Earth gravity returns all at once. The body has to rejoin the environment it spent years adapting away from. We should not make this sentimental. The body is part of the vehicle system. It has tolerances, failure modes, and real unknowns. A mission can keep a mechanical path home while underestimating the human readiness path. If the crew cannot safely execute ascent and re-entry and recovery, the exit is not fully preserved. Here is why medical monitoring and exercise systems and conservative timelines all become return architecture, not merely crew health support. The body also affects decision-making. A marginal vehicle risk may be unacceptable for a compromised crew. A medical condition may force the crew to consider leaving before the preferred window if the architecture allows it. So the return chain is no longer only metal and propellant, and it is biology under constraints. Mars has changed the people who are trying to leave it. Here is also why mission duration matters. A short stay, a long stay, and a settlement scale residence are not just different amounts of time. They may be different biological experiments. The longer someone lives under Martian gravity and radiation conditions, the more cautious we should be about assuming Earth return is a simple medical afterword. The body keeps its own mission log, and that log does not stop accumulating. And the sharper medical problem comes next. What happens if the body needs help while help cannot arrive? If the body can fail on the way home, then medicine itself has to become more independent than it has ever been in human exploration. We have followed the return chain from the surface into orbit and then back toward Earth, and the machine side now has a shape. The question still open is whether the people inside that machine can stay medically returnable when rescue has become a signal, not a service. The International Space Station is far away by ordinary human standards, but medically it is still close to Earth. Crews can speak with ground teams in near real time, and a return vehicle can bring people back quickly compared with Mars. Resupply is difficult but routine in the logic of space operations. Mars changes the category. A 2024 paper on Earth-independent medical operations describes the basic problem. Communication delays can reach about 40 minutes round trip. Evacuation can take as long as the mission itself, and resupply is all but impossible in an emergency sense. That means medical care cannot be only Earth-directed. The crew needs more autonomy, which means onboard diagnosis, treatment, and decision-making authority under delay. Let's slow down here, because the word autonomy can sound abstract. The phrase means a crew may have to decide what is happening inside a human body without waiting for Earth to walk them through every step. The phrase means the medical kit has to cover conditions that cannot be evacuated quickly. The phrase means uncertainty has to be handled on Mars time. And Mars time is unforgiving, and a medical crisis does not make Earth closer, and it does not create a launch window. It does not repair a return vehicle. It does not fill propellant tanks. So the medical problem folds back into the return chain. And if someone is injured or ill, can they wait for the window? Can they tolerate ascent? And can they survive the return transit? Can the rest of the crew operate the systems while caring for them? Those are not dramatic hypotheticals. They are the ordinary questions of remote medicine, stretched across interplanetary distance. We should be fair. Space agencies know this, and Earth-independent medical operations are studied, because planners understand that Mars cannot be supported like low Earth orbit. The issue is not ignorance. It is the depth of the requirement. The return architecture has to preserve more than a vehicle pathway. It has to preserve a medical pathway. A crew that is technically not stranded may still be practically trapped if the human condition and the calendar do not align. So here is where we stand. We have traced the mechanical chain from rocket and propellant through orbital handoff, and we have traced the human readiness chain from gravity adaptation and radiation through medical autonomy. The remaining question is what it means ethically if the chain exists only conditionally. Here is where the word rescue reaches its limit, and on Mars, rescue may not mean someone comes. It may mean the mission had enough foresight that the crew still has options. And if options are the ethical core of return, then a weak return architecture becomes more than a technical weakness. It becomes a consent problem. Here is where one-way Mars enters the story, not as a slogan but as a consequence. The communication delay changes the texture of care. A doctor on Earth can advise but not converse in the normal sense during an urgent event. By the time a question and answer cross the space between planets, the situation may have changed, and that pushes authority onto the crew and onto the tools carried with them. Medical autonomy also changes supply philosophy. The mission cannot carry a hospital, or every drug and specialist needed for every contingency. Choices have to be made before launch, and those choices define the medical edge of the return chain years before any crisis arrives. Now, medical autonomy sounds like a support topic. For Mars return, it is central. A mission that cannot be rescued quickly has to treat diagnosis and triage as part of the architecture, not as something Earth handles later. Let's put the distance into human terms. Depending on planetary positions, a message between Earth and Mars can take many minutes one way. A two-way exchange can approach 40 minutes, and that is not a phone call. That is delayed correspondence during a medical problem. So the crew cannot depend on Earth doctors the way a remote expedition on Earth can. Earth can advise, and Earth can help interpret data, and Earth can prepare procedures. But the immediate hands are on Mars or inside the spacecraft. That changes what the crew needs. They need training beyond basic first aid and diagnostic tools that work without a hospital behind them. They need medications and imaging capability. They need enough redundancy to handle problems that do not arrive neatly one at a time. We should keep this narrow, and this is not a general catalogue of every possible disease or injury. The return chain point is simpler. A medical event can close or distort the exit. It can force departure before an ideal window, prevent departure during a good window, or make months of return transit medically dangerous. Now imagine a crew member develops a condition that would be urgent on Earth but manageable with a hospital nearby. On Mars, that same condition becomes a mission architecture question, and can the crew treat it locally? Can the patient tolerate ascent, and can the return vehicle support care for months? Does delaying departure improve or worsen the outcome? We can see no clean separation between medicine and trajectory. The body, the calendar, and the vehicle all speak to each other. And medical supplies are not infinite. Every kilogram sent to Mars competes with something else, and a larger pharmacy or more diagnostic hardware adds capability but also adds mass and complexity. Deciding what not to carry is itself a medical decision, so rescue ends as an assumption. The crew becomes progressively Earth independent, not because independence is romantic, but because physics forces it. The further the mission moves from Earth, the more the crew has to become its own clinic, workshop, and command center. This has an ethical edge. If a mission cannot evacuate people quickly, then participants need to understand not only the headline risk, but the shape of helplessness. They need to know what care is available and what the planet's delay actually means in practice. We can say that without treating astronauts as passive victims, and crews are highly trained adults, they accept risk. But consent is only meaningful when the architecture is honest about what rescue can and cannot do. So medical autonomy is not a side note after the exciting rocket problems, and it is the human version of ISRU. Instead of producing oxygen locally, the mission has to produce capability locally. It has to do on Mars what Earth normally does for a human body in trouble. That is not a small inconvenience. It changes the meaning of medicine. The crew cannot simply ask Earth what to do and wait for immediate guidance. Earth can help with planning and delayed consultation, but the first medical system on Mars is the crew, their equipment, and their judgment under pressure. Earth-independent medicine means onboard diagnosis and treatment under uncertainty, with whatever pharmaceuticals and imaging the mission carried. This belongs in the return video because medical crisis and return timing can collide. A crew member may need Earth care at a time when Earth is not reachable in the ordinary sense. The mission then faces hard questions. Can the patient wait, and can the ascent vehicle be used? Is the window open, and does leaving one problem create another? We do not need sensational examples. The system-level implication is enough. Mars turns medical uncertainty into mission architecture, and on Mars, evacuation is not an action that exists independently of the return chain. Evacuation is the return chain being used under pressure. That means the return architecture has to be judged not only on planned departure, but on constrained departure. What if the mission has to leave when margins are not ideal? What if delay changes a medical outcome? Here is the third argument state bridge, and we have traced the mechanical chain and the human readiness chain. Now the remaining question is what it means if the chain exists only conditionally. A conditional return path may be honest if the conditions are clearly understood, accepted, and engineered around. It becomes ethically fragile when those conditions are blurred by hopeful language. The crew's consent depends on knowing what rescue really means. If rescue means wait for a window, then launch, then rendezvous, then spend months returning, then the word rescue should not be used casually. This does not mean agencies ignore medicine, and quite the opposite, and the seriousness of Mars medical planning proves the point. Responsible planners know that Mars requires a different class of autonomy, and the viewer should feel the change in category. Mars is not an expedition where Earth stands nearby with a larger toolbox. It is an environment where the smaller toolbox has to be enough for a long time. That changes the moral weight of the exit system. If the return chain is strong, autonomy is a risk accepted inside a preserved path home. If the chain is weak, autonomy can begin to look like abandonment by architecture. A medical system also has to survive boredom. Supplies expire and skills fade, and procedures trained intensely before launch can become rusty without practice. The mission needs routines that keep medical readiness alive during quiet months. because the emergency will not wait while the crew relearns what Earth once taught them. Once rescue is no longer immediate, the return problem stops being only engineering. It becomes a question of consent, duty, and whether a two-way mission has quietly become one-way in practice. And once that is true, the one-way question stops being a slogan. It becomes an outcome that can emerge from ordinary constraints. One-way Mars has been part of public imagination for years. Mars One made it explicit. Send people to Mars to build a permanent settlement and spend the rest of their lives there. The useful lesson from Mars One is not that all Mars settlement is impossible. The useful lesson is how easy it is to undercount the systems that keep a settlement honest. MIT researchers criticized Mars One's assumptions in 2014, pointing to life support, spare parts, and cost assumptions that did not close under existing technology. For our question, Mars One matters as a cultural signal. It shows how quickly the public can accept one-way language when the romance of settlement is strong. But the subtler problem is not an openly one-way plan, because a two-way plan can become one-way in practice. Let's define that carefully. Practical exile does not mean the crew was deceived or abandoned. The phrase means the return option depends on future events that have not yet been secured, future launches, unproven production, hardware not yet verified. Things that exist as plans rather than facts. That distinction matters. A declared one-way mission is ethically clear in one way because everyone knows the premise. A conditional return mission is murkier because the language of return remains even if the exit chain is fragile. So the ethical question is not whether astronauts are brave, and bravery is not the limiting variable. The question is whether the system preserves a real choice to come back. What has to be verified before departure from Earth, and what has to be landed before crew arrival? What promises depend on budgets and political continuity years after the launch excitement has faded? These questions are uncomfortable because they are not heroic. They sound administrative, like procurement and maintenance in governance. But those are exactly the things that make return real. A crew can consent to risk and to long-duration isolation, and they can consent to a mission where rescue is limited. But informed consent depends on honesty about what is known, what is unproven, and what is still only an intention. Settlement changes the pressure further. Exploration usually contains return as part of the mission shape. Settlement can gradually make return optional or delayed or socially discouraged. The longer people remain, the easier it becomes to treat return as a personal preference rather than a core responsibility. And this is where architecture becomes ethics. If the exit is preserved, settlement can be risky and still honest. If the exit is weak, the settlement may ask people to accept more than exploration risk. It may ask them to accept a shrinking set of choices. We do not need to moralize this, and the science and engineering are enough. And Mars does not turn people into exiles by being mysterious. It can turn people into exiles when the chain back to Earth is incomplete. That means the last question is practical. What would a real way home have to prove, and not just what would sound reassuring or fit a promotional timeline, but what would actually count? The hardest ethical failures may not look like cruelty, and they may look like optimism. A schedule assumes the next cargo launch arrives, and a budget assumes the next political cycle remains supportive. A return plant assumes scale-up works. Each assumption is individually understandable. Together, they can transfer risk onto the people least able to walk away from it. So honest architecture matters more than heroic language. A crew may accept a high-risk mission if the risks are named, but if the return path is described as available while key pieces remain future-dependent, the moral center shifts. The issue becomes not courage, but clarity. Now, one-way Mars missions are usually discussed as ideology, and some people imagine heroic settlers who choose never to return. Others imagine reckless schemes that abandon people for spectacle. That debate is loud, but it is not the most useful version of the problem. The quieter version is more important. A mission can become one-way without anyone branding it as one-way, the return deferred, underfunded, or made conditional on systems that never fully mature. Let's draw the line carefully, and permanent settlement is not automatically unethical, and many human communities begin when people move somewhere intending to stay. The ethical issue is not permanence by itself. The issue is whether individuals are told they have a viable way home when the architecture does not truly preserve that option. That distinction matters because Mars can blur language. A settlement may be described as open-ended, flexible, or sustainable, and those words sound generous. But if the return path depends on components that have not yet been verified, the choice to leave may exist only in the language of the mission document, not in any physical reality the crew can use. So practical exile is not a dramatic sentence. It is a systems condition that appears when exit is possible on paper but unavailable in lived reality. Now think about incentives. Return systems are expensive, they add mass, and they demand redundancy for hardware that may never be used if settlers choose to stay. In a budget-constrained architecture, the temptation will always be to push some return capability into the future. That temptation has to be named, and not because it makes planners malicious, and because it is how complex projects drift. A requirement becomes a later upgrade, and a later upgrade becomes a future phase. A future phase becomes dependent on the success of the settlement itself. And at some point, the people on the surface are being asked to trust a promise that is no longer anchored to a near-term system. We can also see why Mars settlement stories often skip the return chain. Arrival is emotionally clean, footprints and habitats under an alien sky. Return is messier, because return asks specific questions, including who leaves, on what vehicle, and under what conditions, and the answers are not always clean. Those are not anti-exploration questions, they are pro-human questions, the ones that keep exploration from quietly using people as irreversible infrastructure. Now, consent must be specific. It is not enough for participants to hear that Mars is dangerous. They should understand the ascent dependency and the propellant plan, and the possibility that return may become harder after the mission begins. That does not remove risk, it makes the bargain honest, and an honest Mars architecture would treat the way home as a core settlement system, not as a courtesy feature. Air and power and return capability all sit in different engineering domains, but all of them affect whether people remain agents inside the mission. We should not use Mars 1 as proof that all Mars settlement is impossible, and that would be sloppy. Its value is different. It shows that the public imagination can accept one-way Mars before the system dependencies have been fully earned. The more serious risk is quieter. A mission can preserve the language of return while depending on future launches, unproven resource production, or later political commitment that may not hold. Here is practical exile, not a declared sentence but a condition. A person can be on Mars with return theoretically intended, yet practically dependent on things that are not yet real enough to preserve choice. The ethics are not about whether astronauts are brave. Astronauts have always accepted real risk. The question is whether the system honestly describes the risk and preserves the promised exit as far as engineering can. Consent has to be specific. Did the crew consent to a mission with a verified return vehicle, or to one where the vehicle depends on later production? Did they consent to medical autonomy without rapid evacuation? Those are different missions with different bargains. Those are not rhetorical traps. They are the questions a mature Mars program has to answer before courage becomes a substitute for architecture. Exploration and settlement also differ in a subtle way. Exploration normally closes with return, while settlement may treat return as optional, delayed, or socially unnecessary. That does not make settlement unethical, because permanent communities can exist by genuine choice. But choice is the key word, and the system has to preserve the real ability to choose. A person who freely decides never to leave Mars is different from a person who discovers that leaving has become impractical because propellant was not ready, or timing closed, or medical capacity failed. So the return chain is also a freedom chain. It preserves agency across distance. Program continuity matters here. A crew on Mars may depend on Earth institutions remaining committed after public attention moves on. Funding and launch cadence and political will all become part of the background return system. If that background erodes, the surface crew may not see a single dramatic betrayal. They may see delays, revised timelines, and postponed replacements accumulating quietly over years. Here is why honest architecture matters more than optimistic rhetoric. A return option that depends on future confidence is not the same as a return option that has been built, tested, protected, and maintained. The ethical answer is not to avoid Mars, and it is to refuse vague promises. If people go as settlers, say exactly what return means. If they go as explorers, preserve the exit as part of the mission's core duty. We can see a final political layer, and the people making early promises may not be the people responsible years later. Administrations change, and companies change, and budgets change, and public attention changes. A real return ethic cannot depend only on enthusiasm at launch. It needs commitments that survive the long calendar of Mars, because the people on the surface cannot simply step outside the project when the project changes around them. The honest question is not whether a one-way mission could be chosen, but whether a mission can become one-way by failing to protect the exit. So the final question becomes practical. What would a real way home have to prove before anyone should trust it? A credible Mars return architecture has to prove the exit, not merely describe it. The first proof is the ascent vehicle. It has to be on Mars, survive the surface environment, and remain in verified condition when the window comes. It cannot be a future hope attached to a present mission. The second proof is propellant. The mission has to know what is in the tanks, whether it is clean and stored correctly, and whether the quantity meets the ascent requirement with margin. The third proof is timing, and the vehicle and crew must be ready when the return geometry opens. A rocket that is ready after the window closes is not a way home. The proof is a delayed promise. The fourth proof is the orbital handoff, and the ascent vehicle must reach the right orbit. The return vehicle must be there, healthy, and able to accept the crew. The transfer from surface escape to Earth return has to be a designed system, not a hopeful meeting. The fifth proof is the human pathway. The crew must be medically capable of launch, transit, and re-entry. If the machines can return but the people cannot safely use them, the chain is still incomplete. And one more proof sits around all of the others. The program has to preserve return over years, which means funding and operations and governance all have to protect the exit from the quiet degradation that follows when attention moves elsewhere and budgets compress. We should avoid turning this into a checklist recited for effect, and the real point is simpler. Every link has to remain real at the same time. A Mars mission can tolerate difficulty, and it cannot tolerate pretending that disconnected achievements form a return chain. A rocket without propellant is not an exit, and propellant without a window is not an exit. A window without a healthy crew is not an exit. A plan without continuity is not an exit. Here lies the boundary between exploration and practical exile, and exploration can be dangerous, and the cost can be high. It can involve long periods where rescue is not possible, but it preserves return as a designed capability. Practical exile begins when the return remains a word while the capability behind it becomes conditional. And now the opening image changes one last time, and the return rocket waiting on Mars is no longer only a machine. The proof is a test. It asks whether the mission has treated leaving with the same seriousness as arriving. If the answer is yes, then Mars can be approached as a place humans may visit, build on and leave. Still risky, and still demanding in ways the first landing was not, but honest. If the answer is no, then the first settlers may not need anyone to declare the mission one way. The architecture may do it for them. Mars does not just need a base, it needs an exit, and that exit has to be real before the word home means anything at all. A real exit architecture would also have to be boring in the best way, and it would have documented margins, it would have test results, and it would have failure modes and responses. It would not need to sound visionary to prove itself. It would be convincing because the chain had been reduced from hope to verified capability. And that may be the deepest answer to the title. Getting there is hard because spaceflight is hard. Coming home may be harder because it asks the whole system to remain honest after the symbolic victory has already happened. Arrival is the moment the world sees. Return is the promise the crew still has to live inside. Now we can turn the whole documentary into a checklist, but not the shallow kind. A real way home is not one green light. It is several independent proofs that overlap at the right time. First, the ascent vehicle has to be more than present. It has to be healthy. That means its tanks, engines, and avionics have survived the surface environment and still meet the launch case. Second, the propellant has to be real. If imported, it has to remain stored and usable. If produced on Mars, the production system has to make the required quantity, at the required quality, with enough margin that the crew is not betting on a best-case number. Third, the calendar has to be respected. The architecture must know what happens if a departure opportunity is missed, shortened, or medically complicated. A plan that works only when nothing slips is not a return plan. It is an optimistic schedule dressed as a commitment. Fourth, the orbital handoff has to be robust. The ascent vehicle must meet something that can actually take the crew home. That receiving system needs power and life support, and contingency logic, not just in its design, but in its actual state when it is needed. Fifth, the human system has to be inside the proof. The crew's bodies and medical readiness and rehabilitation path are not soft considerations after the hardware is done. They are load-bearing parts of the return. Let's be clear about the standard, and the standard is not zero risk, and human spaceflight does not offer that. The standard is credible reversibility. A crew can choose Mars only honestly if the mission has done the work to keep leaving Mars within the realm of practical action. That standard also suggests a sequence. The safest architectures may be the ones that refuse to send people until major return components are already in place and verified. A filled oxygen inventory before crew departure is different from a plan to make oxygen after arrival. A tested ascent vehicle status before landing is different from a promise to repair one later. So proof should arrive before dependence, and that is one of the strongest principles in the entire topic. Now, this does not make Mars less worth exploring. In some ways, it makes the project more serious, moving the conversation away from slogans and toward the true shape of the challenge. Mars is not just a place to reach. Mars is a place that must be entered without surrendering the ability to leave. And once we look at it that way, the phrase coming home changes, and it stops sounding like the closing scene of a mission. It becomes a system that has to be built and protected long before the opening scene. The return chain asks for humility from everyone involved. It asks engineers to prove what the stories assume, and it asks mission planners to treat propellant, orbit, and consent as one connected reality, rather than a sequence of problems solved by different teams. It asks the public to understand that a beautiful landing is not the same as a complete journey. So if humans build a lasting presence on Mars, the most important early monument may not be a dome, a flag, or a rover track. It may be a working exit, a verified ascent vehicle, with verified propellant, tied to a verified way through orbit and back to Earth. Third, the timing has to align. The vehicle and propellant have to be ready when the return window opens, or the mission has to carry a clearly engineered alternative. Fourth, the handoff in Mars orbit has to be real. The ascent vehicle and return vehicle must meet as one integrated event, not as separate optimistic diagrams. Fifth, the body has to be part of the plan. A crew changed by transit and partial gravity and radiation still has to launch, transfer, and return. That sequence has to be planned for honestly. Finally, the program has to preserve the option over years. The way home is not just machinery, it is continuing support and funding and institutional duty that survive the long calendar of Mars. If those things are true, Mars settlement remains dangerous but honest. People may accept the risk with open eyes because the architecture has preserved a real choice. If those things are not true, the mission may still use the language of exploration. It may still have diagrams that point back to Earth. But the practical status of the crew begins to change. Here is why the return question is separate from general Mars survival. And Mars does not only need a base, it needs an exit. The exit has to be protected from the very pressures that make Mars difficult. And mass pressure tempts planners to defer hardware. Schedule pressure tempts programs to accept unresolved dependencies. Budget pressure tempts institutions to push return risk into the future. A serious architecture resists those temptations, and it says the way home is not the leftover part of the plan. It is one of the conditions that makes the plan morally and technically coherent. The rocket on Mars now means more than it did at the beginning. At first it looked like a machine that leaves. Now it looks like a test of the whole system behind it. Its tanks contain chemistry and its structure contains design. Its readiness contains the crew's ability to say Mars is still a place they can leave. Here is the transformation the title was pointing toward. Coming home may be harder than getting there because arrival can be concentrated into one mission arc, while return has to survive everything that happens after arrival. The hard part is not only the launch from Mars, it is preserving the conditions under which that launch still matters. A real way home would be visible before departure from Earth and measured on Mars. It would be protected during the surface stay and timed against the planets. It would include the human body as well, not as an afterthought, but as part of the proof. Here is a high standard, and it should be high because the word round trip is a promise made to people, not to machines, and proof has to stay current. A verified ascent vehicle in year 1 may not be equally verified in year 3. A propellant cache checked after landing may need repeated confirmation, and a crew medical profile can change. So the way home is not certified once and forgotten. It is re-earned across the mission, link by link, until the day it is used or deliberately retired. And when we hold Mars to that standard, the question becomes calmer, not darker, and we are no longer asking whether Mars is doomed. We are asking what would make Mars exploration honest. Because the first settlement that can truly say we can leave is different from the first settlement that can merely say we arrived. So we can return to the question we began with. Is coming home from Mars harder than getting there? Not in every narrow engineering sense. Launching from Earth is still immense, and landing heavy systems on Mars is still one of the hardest things spaceflight asks us to do. A human Mars mission would be difficult from the first launch to the final recovery. But as a promise, coming home may be harder, because return is not one act. Coming home means the whole chain remains true after arrival. By now, the rocket waiting on Mars means something different. At first it looked like a simple symbol of return, but now it carries the entire architecture inside it. It needs propellant at mission scale, not demonstration scale. It needs the right window in the sky and a working orbital handoff. And it needs a program that has not let the exit decay while attention moved elsewhere. Here is the payoff of the question. The way home from Mars is a chain, and a chain can fail at any link. This does not make Mars a death sentence, and it does not make one-way settlement inevitable. The honest answer is more demanding than that, and Mars return can be possible in principle and still be fragile in practice. It can be planned and still not be proven. It can be promised and still depend on future systems that have not yet earned the trust placed in them. Here is where practical exile appears, not as a villainous decision and not as a dramatic moment when someone declares that nobody is coming back. It can appear quietly, when return depends on hardware not yet ready, propellant not yet verified, or future commitments that become easier to postpone than to keep. A real Mars settlement would have to face that honestly, and the question is not whether people are brave enough to go. The question is whether the system preserves the choice to leave. And if this video has followed the exit, the companion question is what Mars demands before anyone reaches that exit at all. And that neighboring problem belongs to GNS Space 031, not the route home, but the world people have to survive while the route home waits. The two questions belong together, but they are not the same, and one asks how to live on Mars. This one asks how not to become trapped there. And that is the quiet seriousness of Mars. And the distance does not only make the journey long, it makes every promise slower to repair. A weak return chain cannot be fixed by good intentions once people are already standing under that orange sky. It has to be made real before their footprints are there. So when we imagine the first crew looking back at Earth, the question is not only what they see, the question is what systems stand behind that blue point, keeping it reachable. So the final image is still the same rocket under the orange sky, and quiet, cold, waiting. The honest mission is the one that can answer before launch, before arrival, and before the return window opens. Yes, the route still exists. Yes, the crew can still use it. Yes, home is still a capability, not just a memory. If it is ready, if the propellant is real, if the window opens and the handoff works, then Mars remains a place humans may visit and leave. If it is not, then Earth may still shine in the sky. Here is the standard Mars asks of anyone who wants the journey to remain reversible. But it is no longer a way home,